Hi everyone. So today I'm going to give a very sort of introductory talk on high entropy alloys. So this was a talk I had given to high school teachers at the Carnegie Science Center in Pittsburgh, and it's meant to be very basic. And a lot of people, most of the people in this call are all professors and postdocs. So it may feel a bit below the standard, but it's aimed at sort of introductory people with sort of minimal prerequisite knowledge. So first, I'm going to start with alloys. So what is an alloy? So basically, an alloy is a mixture of many elements with the requirement that at least one of them is a metal, which is you have a base element as your metal, and then you add some stuff to it to make an alloy. And why would we do that? Well, because two main reasons. Your base metal may have some flaws in it, which you may want to remove, or you may want to augment your base metal with some useful extra properties. So, for example, copper and tin put together is bronze, of course, a very historically important metal, a historically important alloy known for its strength, and we use this to make tools a long time ago. An example of a system where you want to offset some undesirable properties is iron, which is of course very strong, very useful, but it rusts when exposed to moisture. But people figured out that if you add chromium and you add carbon and you add some other elements to it, you can prevent it from rusting and you would create stainless steel. Similarly, copper plus zinc is brass, which is again used everywhere. From basically, you have utensils or maybe door handles or instruments, say brass section. And then lead and tin put together is solder, which is used, of course, in electronics. If you want to create connections which are conducting. Nowadays, of course, people have realized that lead is not good for health. So you have lead-free solder, uh, which works in a slightly different manner. Uh, so how do you make alloys? Well, there are many ways to make alloys, but the most basic, simple way to understand it is you choose a base metal. Let's say you're choosing iron. You melt it in a furnace, so you make it molten, and then you add your solute metals, which are, say, you're making stainless steel, you would add chromium, or you would add your other elements, and then you would hope that they mix, which is a very crucial thing. And then once they mix and you have a molten alloy, you would then cast it into a chosen shape, and then you would let it cool. And that way you would get uh, whatever alloy you're making in whatever shape you want it in. There are many ways you could categorize an alloy, and an important categorization that we use is what does it look like once it solidifies. So it could look in sort of two different types. First is a single phase, a solid solution, which means you have a uniform composition of elements everywhere. So, for example, if you, to give a simple analogy, if you have, say, hot water and you put cocoa in it, it sort of mixes nicely and you see a uniform solution everywhere. And that you would call single phase. So there's the one phase everywhere. On the other hand, you could have multi-phase. So you could have systems with different compositions present in the alloy. So I have two images here of alloys taken using a scanning electron microscope. So here you can very clearly see the difference between a homogeneous or a single phase system and a multi-phase system. So if there are different phases in your alloy, and most alloys are multi-phase, then how would you keep track of these different phases and how would you categorize them? So the way to categorize them is this elegant tool called a phase diagram, which is probably the most important uh, tool that material scientists and engineers and scientists in this field use. And it basically allows you to keep track of the different phases with respect to certain important variables. So again, to give a very simple analogy, let's say you have water and you have sugar. So if you have pure water and you put sugar in it, initially it will mix nicely and you won't see any sugar. You'll just see sort of sugar water. But of course, if you keep adding sugar beyond a point, it won't mix. And then you will see some sugar at the bottom of your glass. So you would hit what's called a two-phase region. So you would have a phase of sugar water, and then you'd have a phase of just sugar. And then similarly, of course, you could go from the other way. If you have just pure dry sugar and you just leave it outside, often if you don't put the lid on a jar of sugar, it catches moisture and that sugar sort of becomes wet and sticky. So that is also a single phase region. And then, of course, if it's exposed to too much moisture, then you might just straight away notice some water in your jar of sugar. And then once again, you hit the same two-phase region. And if you increase the temperature, uh, of course, it is obvious that you would now be able to add more sugar in your water. So your two-phase region becomes effectively smaller. And this phase diagram shown here allows you to interpret all that. And that is how phase diagrams work, basically. So we can look at a phase diagram for a real system, which is solder, lead, and tin. So once again, you have a pure lead limit and a pure tin limit. And in when small solute concentrations, you have single phase. And then at high temperature, you have single phase. But everywhere in between, you have two-phase regions. And the way you keep track of the number of phases is what's called the Gibbs phase rule. And here P refers to the number of phases. C refers to the number of components in the system. So here you have lead and you have tin. And F refers to the number of degrees of freedom that you have specified. So here we have specified, so let's say you specify temperature, you fix a particular temperature, and let's say you also specify pressure. It's not mentioned here, but since we're dealing with solids and liquids, it is safe to assume that we are doing everything at atmospheric pressure. So you would say the pressure is fixed at 1 atmosphere. In that case, you would have at max two phases. So, and that is also what you see in this phase diagram. And you can study something interesting here at fixed temperature given by this tie line. So you can see that the melting temperatures of lead and tin are quite high. So one is at 327 Celsius and one is at 232. But if you mix them, so if you get to 60% weight of tin, you can see that the melting temperature is now much lesser. So it's liquid at a much lesser temperature, which implies that you could have a solid tin, which is hot, and solid lead, which is hot. And then if you put them together, they would mix and they would just melt without you adding additional heat to it. And that is called sort of eutectic behavior. And we can see that here. So I have a video here. Basically, there's hot tin and lead, and uh, they have been put in contact together. And then you can see that without adding any additional heat, it has melted because an alloy has been formed, and that particular alloy has a lower melting temperature than the individual components. So this is, in fact, the principle on which solder is based. So solder is uh, solid and it has a low melting temperature when you add these two together. And then you can use that to create liquid, and then um, it solidifies quite easily. So basically, the current alloying scheme that I mentioned is you have a base metal, and then you add additional elements to it in small concentrations. And this base metal is the most important thing. It is the principal element, and it's basically what is prevalent in your system. But what would happen if you have multiple principal elements and you have many different elements in your system? Well, the Gibbs phase rule is directly dependent on the number of components. So if you have more components and your number of degrees of freedom, say, remain the same, then you should have more number of phases in the system. So, and if there, which brings an interesting question, which is even if you have a lot of elements and more possibilities for phases, could it be possible to get a single phase system with many base components? And this is the question that these two professors on the right thought about initially, and they wanted to see whether that was possible. And the principle behind which which propels this topic and made these two professors think that this could be possible is the idea of entropy, or rather high entropy, and for which it's important for me to now define what entropy is and explain the principle. So mathematically, you could define entropy as k log n, where n refers to the number of arrangements in your system. So for example, if you take two unbiased coins, if you have both of them are heads, there's only one way to arrange them. So you have no entropy here. If you have both of them as tails, again, there's only one way to arrange them. But if one of them is heads and one of them is tails, now you have two ways. So the first coin could be heads, or the second coin could be heads. So now you have two arrangements. Your entropy is k log 2. So more arrangements implies a higher entropy. Now, mathematically, it is somewhat straightforward, but physically, what does this mean? And to understand this, let's explore a nice test system, which is, let's say you have a chamber with two partitions, A and B, and there's a solid wall in between. And in A, you have 10 particles or 10 molecules of gas. Now, you take away this partition in the middle and you leave it for a while. And you come back and you want to know how many particles are now in partition A and how many are in partition B. Well, that's without keeping track of those individual particles, it's difficult to know. But once it's equilibrated, it's reached a steady state, you can then have a probability associated with each answer. So the if what is the probability of having, say, 2 particles in A and 8 particles in B, that you can calculate. And you can similarly do that for all the different configurations and create a probability distribution, which is the plot I have on the right here. And here you can see that the most likely state nearly corresponds to maximum entropy, which is having 5 particles in box A and 5 in box B, which is what is associated with most number of arrangements. But the uncertainty is quite high. You're not really sure that the highest probability state is what the system would attain. Now, let's say from 10 particles, you go to a much larger number. You go to 100 particles. Now, the uncertainty is a bit smaller. And let's say now you go to 1,000 particles, the uncertainty is even smaller. So the probability distribution is much more peaked. And it's much more closer to 500 particles in box A and 500 in box B. Now, if you go to 10,000, it's practically a straight line, which means you're very, very confident that once you let it equilibrate, there would be 5,000 particles in box A and 5,000 in box B. Now, which means uncertainty is coming down. But how much is 10,000 molecules, say, in context? Which means, let's say you have a milk gallon and it has a volume of 3.78 liters, and you've left it at, say, 0 Celsius, which is roughly the temperature right now in Pittsburgh, and you're left it at 1 atmosphere pressure, then the ideal gas law tells you there are 10 to the power 23 molecules just in this 1 gallon milk, which is a lot more than 10 to the power 4, which means you can be pretty confident that it would be a very, very sharp peak right in the middle. So you would have half the number of particles in A, half in B, which is, again, the most highest entropy state. So when n tends to infinity, there is no uncertainty at all. So the system will just go to the maximum probability state and it will try to maximize its entropy. And this is what we call a second law of thermodynamics. and it is a fundamental law of nature. And what does all of this have to do with alloys? So if you have more number of elements, there are sort of more ways to arrange uh, your system. So since there are more arrangements, there's a higher entropy, which means the system will try to go to a higher entropy state. And since higher entropy state is favored, it means that you could get a single phase system with many base components. You wouldn't have a clumping of different phases everywhere. You would have a uniform mix because more arrangements are associated with that type of mix. So we can model this mathematically by a concept of free energy, which is defined as delta F, or you could write it as delta E minus T delta S, where delta E is a sort of change in energy and delta S is change in entropy. Now, if delta F is less than zero, it means this process will happen naturally. And if delta F is greater than zero, this process has to be forced, which means you have to apply some external energy to make this happen. Now, if delta S is greater than zero, you can see that because of the negative sign there, this will force delta F to be less than zero. So this mathematical tool of free energy allows us to incorporate the second law of thermodynamics in our equations. So this idea of high entropy makes it intuitive for why we would see a single phase with multiple elements present. But the field of high entropy alloys really took interest with papers like these from 2004. So here on the right, you can see different high entropy alloys with a lot of elements in them and their hardness. So you can see that the hardness of these high entropy alloys is much larger than stainless steel, which we know to be quite hard and quite useful. So this means that
Vishnu, can you just define exactly what is hardness? What is the definition of hardness?
so this is based on something called Vickers hardness. I think it's based on diamond. I think diamond has a Vickers hardness of 1,000. I'm not exactly sure how this is measured. Uh, but yeah, I think it's uh based on applying pressure. I'm not fully sure. I have to check that. Yeah, so basically this is why there's a huge interest in high entropy alloys. It's not just a theoretical notion that you could have single phase with more elements. This could also be quite useful. And some of the alloys here have 8 components and they are still single phase. Uh, Also, generally, the notion is that if something has a higher strength, it would have a lower ductility, so it would break easier. But high entropy alloys uh, can buck this trend. So you can see that with high entropy alloys, you could have system which could stretch longer and also have higher strength, which is again very useful. Uh, and the number of papers in this field has grown quite dramatically. So there's a lot of different research groups around the world working on this, and this is constantly increasing. So this is a very active area of research. So in our group, what we are doing here is a sort of theoretical modeling, because the elements that I've highlighted in this box here are quite popularly used in high entropy alloys. And of course, it's not limited to these. There are many others. And there are many different combinations of these. It is not practical to just test all of them and see which of them are single phase, which of them have good hardness and good properties. And and of course, only some of them will be useful. So it is then important for us to develop simulation tools to simulate these systems on a computer and to test whether these could potentially be useful. And of course, this is fast and relatively inexpensive, mainly because there are a lot of good softwares and there is a high performance computing facilities available, which I'll discuss about. And of course, you're not limited to practical concerns. You can make any type of structure you like. and you can simulate any condition, say low or high temperature, pressure. So that is quite useful. And the basic principles, of course, you have this equation here called Schrodinger's equation, which gives you a quantity called the wave function, which contains all the properties of the system that you could be interested in. So if you solve this equation, it would allow you to calculate all the interesting properties of the system. And there are many codes which are devoted to solving this equation. There's a lot of mathematical theory behind how you can convert this equation into something that's simple and fast and easy to solve. But despite those mathematical uh, progressions, it is still a very intensive process to do these calculations, and you require large-scale computing clusters. So I've given sort of three examples. So one is the Fugaku system in Japan, which as of few months ago was the fastest supercomputer in the world before it was taken over by Frontier in Oak Ridge. And that is a very, very large system. And then you have Bridges 2, which is in Pittsburgh Supercomputing Center, here, of course, part of Carnegie Mellon. And it is also quite large, not as large as, say, Fugaku or Frontier, but still very, very powerful. And then you have Euler, which is a simple cluster that we use in our research group here. And it contains about 10 to 12 nodes. It's used by a few people, but again, it's powerful and can uh, give results. So these are three different scales of clusters that people use. And what all can you do using simulations? Well, firstly, going back to phase diagrams, you can calculate phase diagrams on a computer without having to, again, experimentally find out what phases are there using a technique called CalFAD, which is calculation of phase diagrams. So you would do a CalFAD calculation and then inform experimentalists that certain concentrations would give you a single phase. And then that would be important information for experimentalists to then synthesize that alloy. You could calculate ductility. So you can computationally stretch an alloy, and you could calculate how the energy changes and how the stress changes. So here you can see that beyond 10% strain, the stress comes down. So if on increasing a strain, the stress comes down, it means that there's some mechanical instability there, which means the system is likely breaking there. So at that point, we would then do further analysis to see how the system is breaking. And again, this could be very useful information to give to experimentalists when they are doing tensile tests of alloys. You could also calculate electrical resistivity, which is again a very important property. So here is an electrical resistivity of aluminum, cobalt, chromium, iron, nickel. And here you can see that this system has sort of interesting behavior in this middle intermediate region. And our computational calculations can recreate experimental trends. So which means we can get accurate electrical resistivities using computational tools. So what is in the future for this field? Of course, easy and inexpensive manufacturing is still an ongoing problem. It is still, of course, much convenient to manufacture more simpler alloys like steel, and people are still figuring out how to manufacture high entropy alloys. So that is a barrier to then them replacing conventional alloys in, say, construction. A better understanding of the physics is still needed. There's a lot we don't know about why high entropy alloys work the way they do. Of course, the entropy is sort of one intuitive way to understand it, but it's also important to understand that simply putting large number of elements won't necessarily give you a single phase. You're more likely to get a single phase, but you should also choose those elements carefully. So if you choose similar type of elements which are same crystal structure, which are of a similar atomic size, maybe you're more likely to get a single phase. So there's a lot more we don't understand, and there's that's an ongoing research problems. And of course, there are applications for clean energy production and storage. For example, one of the programs that our group is involved in is to design ductile turbine blades at high temperature, which would then allow those turbine blades to be more efficient and generate more energy and have less waste. So that's all I have. So if you have any questions, I'll be happy to take them.
Thank you, Vishnu, for the great talk. Yeah, let's ask questions. Very nice. Okay, great.
Yeah, very nice. It was very informative. I actually learned a lot.
Yeah. So any questions? Go ahead.
So I would like to ask, concerning this ductility. So my understanding is that from what you explained, there's a linear response of stress of strain, which is like the elastic response, but then past that there are some plasticity or defects or the cracks or something happening. And computationally, how exactly is this done? You alluded that with your setup you can computationally address this issue, but how exactly is this studied technically? I mean, can you just kind of explain in words?
Essentially, so in our calculations, we can define a geometry file, so which we would define all the positions of your unit cell, and you would specify your lattice vectors. So if you then just change one of those lattice constants, so if you want to stretch a system along Z, so you would just change the lattice constant in that direction by say 5% or 10%, and then you would recalculate. You would redo a DFT calculation, and then get a relaxed structure at that stress at that strain, and then calculate the forces and calculate the energy. Then from that you can then get these type of plots.
But do the atoms remain periodic, or you're allowing some, defects to be generated, like dislocations?
We are allowing, so they don't have to be periodic. So, and often there can be quite a bit of lattice distortion.
So is this in a supercell with a supercell calculation? How
Yes,
big
this
is
is in
the how big is the
so
supercell?
so these were done with a 128 atom supercell. But yeah, generally 128 to or 250 atoms
Very nice.
is what we use. Yeah.
And
supercell itself repeats itself, so it's
right.
In large scale it's still periodic.
Yeah.
But simpler things like CPA or effective medium, various effective medium theories that probably cannot deal with this. Is there any way to improve effective medium theories or something simpler like that to learn about this ductility?
I think in CPA you can deal with substitutional. So if an atom is slightly off the ideal side, so there is a way to deal with that with CPA, but it is of course much more, I think, straightforward to just create a large supercell and just do those calculations.
Yeah, I think the CPA usually deals with like a substitutional disorder. If there's a small displacement, I think can do like embedding. It still treat the effective medium on underlying lattice, but some particular atoms can have less displacement. I think that's doing some kind of embedding calculation. I think that's how it's done. But for a large unit cell like this, I don't think CPA could do it. I don't know. If there's no displacement, you only stretch the unit cell. I think CPA.
I did a project recently where it was fully about this ductility, where we were stretching different elements and trying to analyze what happens in terms of electronic structure. So I'm happy to talk about that next time.
Right. I'm trying to get an idea. Like people talk about how metals are soft because the dislocations, very clean metals, they'll be very soft because these dislocations, they can perform some kind of diffusive motion. So if you define objects like these dislocations, you can think of this, they are flowing with, it's almost like there is a an effective description in terms of these defects, moving around, performing diffusive motion, which does not, I think in the old days they didn't have these very powerful computations, but they had some understanding, I think, of the plasticity, or this is at least my impression. I don't know much about this. Maybe Malcolm can say something about that.
Well, there are, one of the things that we did early on, back in the, well, let's forget when back in, you can use the CPA to get the energetics of the totally random system, right?
Mm-hmm.
And what we did early on was to say, okay, let's imagine that is that at high temperature, then what you can assume is that this is the most disordered phase. The higher the temperature you get, the more random it becomes. And what you can do is you say, well, what I can use is I can use the CPA energetics as a description of the ideally disordered alloy at high temperature. And what you can do then is to say, at lower temperatures, does the energetics allow you to have more than one phase?
Mm-hmm.
And we developed a whole theory along those lines, and it turned out to be very, 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 very useful.
Mm-hmm.
Of course, in the end, what you have to wind up doing, no matter what you do, is so. What we did. Well, let me just say one point. We have the CPA as the description of the ideally infinite temperature disordered phase. And then you can look for the instabilities in that, right? And that's basically what this approach that we developed does, and it works quite well.
Mm-hmm.
But in the end, at some point, you are effectively comparing the energetics of in disordered systems, like what he's been talking about, where you have multiple phases. Then you kind of have to deal with all of those phases, right, and compare their relative stability at any given temperature, right? Of which the disordered phase may, in fact, be the ground state. Or the stable state as you come down from high temperature to lower and lower. And of course, then at some point, if it's a complicated alloy, you will get multiple phases that occur at different concentrations. And so you're kind of stuck with having to deal with all of those. And that eventually then becomes a lot of first principles calculations.
But I'm sorry to interrupt all the time with questions, but I just want to understand one thing. Maybe you can explain, Malcolm. At final temperature, there is the contribution to the free energy coming from electronic excitations, but there are also the vibrational excitations, right, which contribute to the stability, I guess, right, of various phases. So how are these included in this kind of, for example, if you do supercell DFT, do you have to do molecular dynamics or what?
Well, I mean, the molecular dynamics is the sort of brute force approach to doing all of these problems, and so at some level everything dissolves into that.
Right. But can you do something else?
Say again?
Can you do something simpler?
You just calculate the energetics of the various phases, and then you've got to write down an expression for the free energy of the system, right? And then study how the free energies vary as a function of temperature and composition.
But you have to add the free energy of the phonons.
I mean, there are systems. There's some, I think it's zirconium alloys, which are quite anomalous. That those things will undergo a phase transition, which is driven by that. So, but at all, again, you know, you're just stuck with that final problem unless you do molecular dynamics, right? And of course, for molecular dynamics, one is you get doing that ab initio is a very tough problem, and so what people do is to make, again, models, right, with various terms in that represent the various states of the system that you're actually looking at. So, you know, I mean, you don't. We tend to look at phase diagrams and only look at the ground state. We don't ask too much, or the state above the phase transition. But again, the macroscopic behavior that's of interest are things like you take these materials and put them under stress. And some of the things that you find is that they then, with stress, you start getting multiple phases that you didn't have, right?
Oh, yes, I see.
And so, and the same is with entropy, with the vibrational entropy. And of course, we can you know, deal with the vibrational entropy in these kinds of alloys by, again, with supercell calculations. You can calculate the phonons, and with a number of papers in which we do that. And you know, again, it's just an approach that allows you to do a pretty good job of figuring out what the phonon spectra look like. And one thing that kind of died the death in CPA was, you see, originally when it was formulated, it was kind of assumed that the CPA would apply perfectly well to alloys with the electrons and the phonons themselves, because you put some second element in and you muck up the phonons, and so the phonons, when you've added some other element, they are become you know, in the infinite system, there is the phonons have got a width to them, and you can set up the equations for the phonon spectra where that can be taken care of. And the problem with it is that when you convert that to a CPA-like language, it becomes incredibly complicated, becomes very, very complicated, and we've done things in that, and other people have, many other people have. Yeah, and I think that's probably enough. One of the things that we looked at with these high entropy alloys was that again, you know, it matters with the phonons. Well, one of the things that's difficult within the CPA type languages is that we can't deal with atoms or it's difficult to deal with atoms that are not on the lattice, and in the simple models, what one does is one says, well, you know, there's a point energy to do with the atoms, and then there are terms which couple an atom on site A to an atom on site B, and so those could in fact be different from one another. So in a binary, just have AA and AB and BA. But again, to make the solution of the CPA equations easier, initially it was assumed that, so we've gone the site energy, you just call the single site energy, and then the other one is the hopping term. And what one says is that we assume that the hopping terms, the AA, BB, and AA, BB, and then AA and all and A. The hopping integrals, the hopping components are satisfies either are all the same or satisfy some simple simple rule, and people have been able to develop that. But again, what we found in these high entropy alloys is that the fact that the atoms are of the tend to be the AA and BB and whatnot, hopping integrals tend not to depend upon the local configuration. And so you can't just have a very simple Hamiltonian with only, say, the site energy and the hopping integrals fixed, and then you just compute, and that turns out not to be good, and particularly bad when the systems where the lattice site positions are very sensitive to the local configuration. So if you have an A atom surrounded by B's and then B's surrounded by all A's, those for the hopping integrals alone, that those are not the same, and then you're kind of stuck again.
Right.
That's a lot of rambling. I don't think it's. But we always like we tended to think of the CPA as the high temperature phase, even though we and lots of other people use the CPA as if it gives the energy at zero temperature, gives the ideal energy of mixing, and that's not what the CPA is about, right? If you think about it, it is dealing with the ensemble, and where that approximation that the system is disordered but homogeneous is in fact only given to be one assumes that is actually describing the high temperature state, and then you can build a theory on the instability of that disordered phase at high temperature, and yeah.
Thanks a lot.
Okay.
Question maybe? Yeah.
Other questions?
Yes, can I have a question?
Sure.
Yeah. So, for instance, if I see the phase diagram for instance, one with the trigonal, the other one with the cubic phase, and so on. So, how do we compare that in the temperatures in different range of temperature and I would say pressure, for instance? If we have the same pressure and then different at the same temperature, and then we just compare with the two different crystal structure that we put it on, and then let them relax, or like how is technically?
Yeah, so you create different structures and then you treat them differently.
Okay, so you keep the symmetry for the temperature, like doing vibrational calculation.
So that's an easier way. I mean, you could also, as mentioned, create a really large supercell, and then if you do molecular dynamics at different temperatures, you will see the change in crystal structure.
Oh, so you let them change by itself, so you don't constrain the volume.
Yeah, you can do both. So if you know that these are the two phases that exist, you can create separate structures for these two and then look at them separately. But then
compare the energy.
Then you can also create a really large cell and then do MD at different temperatures. And then if you look at the results of that MD, you'll see that below temperature, it'll look a certain way, and above temperature, it'll look a certain way. So then you will be able to see that phase transition in MD, even though that's very expensive computationally to do.
Okay. So for the empty, you let them relax. Depends on what your initial structure, right? Because the positions of the different atom cannot be switched to each other. Like they cannot swap between each other. They just move with the
Yeah,
empty.
I mean, yeah, with MD, there are small movements, and then
Mhm.
it
Okay.
sort of changes structure.
Okay.
Again, the problem always is that with molecular dynamics, if you have to you're simulating the disordered system on a very, very, very short time scale, and waiting around for things to happen on the inside that actually correspond to, say, even one hopping from one atom from site A to site B. You have to do a lot of molecular dynamics simulations in order to see that, unless you do it at very high temperature, right?
Yes.
And so, which is why people then go and construct classical potentials, effective potentials, which describe the interaction between pairs of atoms. And you have to parameterize it somehow, and then you can effectively turn the time scale at which you're simulating up by multiple orders of magnitude, and in that kind. But even there, it was a tour de force to be able to see these kinds of motions actually happening. Right.
So to actually look at timescales at which these reordering of atoms happens, you'll have to go beyond just molecular dynamics, where you solve Newton's equations for the movement of the atoms, but actually add a bit of the thermal excitations, or the probability of this, using something like a kinetic Monte Carlo, where you say, oh, there is a certain area height in the energy landscape that you have to overcome for atoms to move to new lattice positions, and then you associate a time scale with this movement, and that then allows you to do simulations that go to actual time scales where you see these reordering of atoms actually occurring. Just normal molecular dynamics at temperatures you're usually interested in. But even with a classical force field take a very long time.
So Marcus, this is not true. It's not the same in all systems. Like in simple systems which order like ferromagnets, well, that's Monte Carlo can be done very easily. But if you have a somehow glossy ordering and a lot of frustration, then even Monte Carlo methods can be very difficult to do. So it's not always the same. And it begs the question: in these maximum entropy alloys, you have many configurations. Are just on a classical level, like on the level of these classical potentials that Malcolm is mentioning, is this a huge computational problem just to equilibrate this alloy starting at high temperatures? Is this more difficult than a regular crystal or binary alloy, or not?
In principle, not. Well, it depends on the level of theory you're trying to do, but in the sort of base level, no, you just have to, do all of these supercells or whatever it is you're trying to do.
I understand that technically you can do it. It's just the question. I'm saying that, if you study different, say, classical systems, they don't equilibrate at the same rate. Some systems have a much longer relaxation times, right, than others. And the same technique that you use, it will not work. For example, for spin glasses, people have had a very hard time equilibrating them and so forth. Now, I was wondering, are these maximum entropy alloys in this category where you have a hard time relaxing, or maybe it's the opposite? Maybe they relax faster. than simpler systems.
Yes, sometimes you get
I've noticed that at low strains, I've relaxed quite a bit of 5 and 6 element high entropy alloys, and they don't take much time to relax. But at higher strains, it becomes really difficult. So at almost 15% strain, I just could not relax a 6 element high entropy alloy in practical time.
So is this compression or it's stretching? Is this compression?
No, stretching.
Stretching. So you're saying when you actually stretch it, it has a harder time relaxing?
For high entropy alloys.
And do you understand?
I've observed that.
Is there a simple physical picture? Why is that? What exactly is the
Because I think
bottleneck?
in simpler crystals, there's not that much, but I think that much happening. But in high entropy alloys, I think there are dislocations and there are more defects when you relax at 15% strain, which is quite large.
You know, this is an interesting question because, you know, I've heard that metallic glasses, for example, are harder mechanically because they don't have dislocations. The dislocations tend to move easily around when you have crystal planes. But when you have an amorphous system or a very random system, then these dislocations can tend to get stuck. This is why apparently tempering iron with carbon, you know, or not tempering, I mean, when you make steel, right, you are like putting defects, and these defects, they prevent the dislocations from moving around. You'd think that these entropy alloys would be like that, right? That they would have the dislocations will be a harder time moving around. Are you saying that in the opposite? Is that what you're saying? That they move around more, or there are more of them, but they don't move around?
So it probably depends on. So if you have an alloy where you have a strong sort of relaxation of local atomic volumes, basically sort of in the I think metallurgist language, atoms of very different sizes, probably will have a very strong solution strengthening effect that would prevent the movement. But if that's not the case, actually probably the opposite would happen, because in this ideal solid solution, so another effect is that can lead could lead to strengthening is sort of due to local short-range order. So if you imagine a system where you have local short-range order that is preferring one bond over another, and you move atoms with each other, you'll change this local short-range order. If you have a system where there's basically no short-range order, like in an ideal solid solution with equal concentration, basically nothing will happen because it is sort of, if you squint, isotropic. So that probably would not lead to a hardening of the material. So there are probably two different effects, one reducing and the other one increasing, and it depends on what's the more important.
Okay, other questions? I'm going to stop recording and you guys can have a free talk.